Hello! In this video I want to just talk about this thing called phase portraits. I think a lot of people are put off by phase portraits, but I want to talk about them and show them actually why they're really useful. Maybe I'll talk about why I'll talk about why they're useful now, actually. I'll treat you. So, phase portraits are useful because if we have a really complicated ODE, we can represent that ODE graphically, fairly straightforwardly. And I'm going to show you how we would do that. We consider kind of the nature of equilibrium points and things like that, and what happens around those equilibrium points. And we have to use things like eigenvectors and eigenvalues, but I'll show you all those later. But basically, just believe me for the moment, all you need to know is that if we have an ODE, what's going on? Thank you very much. If we have an ODE, okay, we can draw what's going on graphically. So in other words, we don't even have to solve the ODE, because the ODE could be really, really difficult to solve. You know, ODEs become really difficult to solve. It's like if you have polynomials, okay? You know, x squareds in general. You know, polynomials involving x squared. So like x squared plus 3x plus 2, and you set that equal to 0. That's relatively easy to solve. X cubed plus 4x squared plus 2x plus 10. Set that equal to 0. So now we're looking at x cubes. They're okay to solve. It can be done. X to the power 4, okay, that can be a little bit more difficult to solve, but we can do it, I think, numerically. As soon as we get to now x to the 5, the only way to do it is just by fiddling around and just playing with different numbers. So in other words, finding out which values of x equals, when we plug it in, it equals 0. But the only way we can do it really is by graphing it and then just guessing, by putting in different numbers, so the numerical solution. So in other words, there's no what we call there's no way that we can solve an equation. Like here, we've actually got an equation, and we get the equation just by rearranging it. So it's x equals minus b plus or minus the square root of, b squared minus 4ac all over 2a. So we can actually get an equation like this, and this isn't that difficult to solve either. We can get it by using things like the factor theorem, and we can also use matrices as well if we want to, definiteness and things like that. But anyway, you know, I digress. Basically, if we have a really difficult ODE that we have to solve, and if it looks really nasty and we can't solve it, okay, so in other words, a high order ODE, we can plot it graphically. You know, plotting a function graphically isn't that difficult. Okay. You know, nowadays computers can do it quite happily. But if we can plot an ODE graphically, we can kind of see what the solution should look like. And that's quite a lot of the time all we want from an ODE. So we have an ODE, for example, what we want from it is just what the solutions are doing. We're not necessarily actually interested in what the solutions are. Like, we're not interested in what, like, the number which the solutions are. We're just interested in what the solutions are doing. And so this is why phase portraits is really useful. Okay, so let's say we have a function, y, which is a function of t. So in other words, y will change through time. And then if we differentiate it, so we differentiate y with respect to t, okay, and then I'm just going to call this a function. And this function is going to be f of y of t. You happy? Because this is of t as well. So our function which we're going to get is going to be of y, which is going to be of t. Okay, but just for convenience, I'm just going to denote this as f of y. So essentially what I've got is I'm going to get dy by dt. This is an ODE. dy by dt equals f of y. And I've basically now set up an ODE. So this is all I'm considering now. So dy by dt equals f of y. If you want a little bit of substance to support that, let's suppose, for example, y is a function of t. So what we're going to end up with is y equals, let's say, 3t squared plus 2t plus 3. I'm literally just making this up now. Then if we differentiate it with respect to t, what we're going to end up with, well, this is going to be, what's it going to be? 6t plus 2. All right. Well, are you happy that that is a function of t, but it's y as a function of t? So this is y as a function of t, okay, because it's got t's involved there. So we differentiate it, we got y as a function of t, and I'm just going to call that some function. So this function, this is a function of y, which is a function of t, but I'm just going to, for convenience, drop the t. All right. So this is all that's really going on. You can stick this over here if you want to consider that and absorb that as we go along. Stick that there. Alright, So basically, let's go back to this thing. So we've got y as a function of t. What does that mean? It basically means that y changes through time. T in this context means time. Okay, it's a variable which means time, and that's convention. Whenever you see a t in your maths equations, it normally means time. And if it doesn't, somebody's been very silly and very careless because they haven't used the correct variables. All right, so this is a function of time. So in other words, y, let me just write this down, the value of y changes over time. So if I want to express that on a number line, I can do that quite easily. So I've got a number line here, and this number line is y. Okay, y is t. So it just shows how the value of y changes through time, because y is just going to be a number, right? So it will change through time. So let's say at time 0, so y of time 0 is going to be 0. Okay, and then let's say it goes to another value at y of time 1, and then it goes to another value at y of time 2, then it goes to another value at y of time 3. Hopefully you get the idea. Basically what happens is the value changes, right? And we can also, and in general we always go to the right, but essentially this is known as the phase space of y. That's known as the phase space of y. Alright, so we've got this. I'm going to stick this now. Thank you very much. I'm going to stick this over here. And I'm also going to change this down here as well. I'm just doing a little bit of tidying up so it looks a little bit neater, so that you guys can have a nice little look at it and you can enjoy it. Alright, now I'm going to introduce a couple of terms now. And these terms can be quite technical, but don't worry. I'm going to introduce something called an orbit. Now, the important thing is the idea, not the name. Okay, so if you understand the idea, then it doesn't matter if you don't remember the name. So don't be put off by the name. But an orbit, well, let's just think of a space rocket. Okay, a space rocket goes out into space. Okay, and it goes into orbit. Okay, so in other words, it's something which moves around. Okay, so everywhere that the rocket goes, that's known as the orbit which it's in, or the satellite, or whatever object you want to consider. Let's call it a rocket. Everywhere that it goes is called the orbit. It's exactly the same with an ODE. It's all the points, or the set of points, but all the points which are visited by our ODE. Okay, so all the points which are visited by this thing. All right, and if we can, so that's all an orbit is. It's just basically all the points that are visited by our ODE. All right, and we can model that using using the same thing as we use down here, the phase space. So t ranges over all the possible values. So in other words, we get some y values out. So let's say we start here at some point, and this is going to be t. So this is, say, like y of t1, okay, at time 1. And we're just going to call that t. Likewise, like the thing which we did here. So y of t is equal to some function. So I'm just going to call that function. So the y of t1 is just going to be t. Okay, but then let's suppose at y of t2, so the next point of time, I'm now at t plus h. So in other words, I've moved by some distance h. Right, so I start at my function which is given by t, then I move to another point which is given by t plus h. Right, there's a lot of t's and stuff going on, but hopefully you can follow the notation. The idea is what is important here. So we start at t at time 1, and then at time 2 we move to t plus h. So we've moved by a distance h. Well, what are we doing here? Well, what we need to do now, we're trying to basically build a connection between this thing which is called an orbit and this thing which is called a solution. So the solution is like the answer which you get, so like what the ODE actually is, all right, and how we can summarise all the points. So the orbit is all the points visited by ODE. A solution is like the summary of all those points, like written in one neat little equation, if you like. Okay, so we need to determine how the point y moves through its orbit as t increases. So in other words, what happens as t moves. So in order to do that, we just consider these two times. So time 1, we're at t, time 2, we're at t plus h. Hopefully you're following. I realise I've just said the same thing many different times, but hopefully it's starting to sink in. Let's just assume that this time step is small and positive. All right, then what we've got is that the change in y, so the change, let me just write this out actually, change in y with respect to time, with respect to the change in time. So notice that the change in time is just moving from t1 to t2. All right, it's a bit like moving from 2 o'clock to 3 o'clock if you're moving in the space of an hour, or from 1 second to 2 seconds. So we're moving from time 1 to time 2, that's the change in time. Okay, well we know that in the change of time, where are we moving, how much are we moving in that time period? So we're moving from t1 to t2, that's the time period that we're moving through. Well, what distance are we moving through in that change in time? We're just moving through h. Okay, so are you happy that that change in time is just given by h? Then what have we got as a change in y? Well, it's going to be y of t plus h, because it's a function now, y of t plus h, minus y of t. Yeah? Because at t1 equals t, and t2 is equal to t plus h. So therefore, y of t1 is going to be y of t. Sorry, no, this is y of t2. So now I'm laughing because it's if you understand differentiation from first principles, this is easy. If you've never done that, go back and watch my video on it. I'll stick one up for you because I'm nice like that. All right, but basically what we're doing is the change in these two time periods, the change in the y value is going to be this one minus this one. It's yeah. Hopefully that makes a bit of sense. Go back and watch my thing on, my thing. Okay, well this is an approximately equal to, because of course h is a small positive thing. What we basically want to do is try and decrease that to make it equal to 0. So basically make this time smaller and smaller and smaller. Don't worry too much about that. What we're going to do now is just write this change in y of a change in time sort of more mathematically. Remember that the symbol in mathematics for change is delta. In science, is delta. Right, well, we're considering a really, really small change. Let's just assume that h is a really small positive integer, but really, really small. Okay, well, if it's really, really small, then we're going to use this one, little delta. Makes sense. We've gone from a capital to a small letter because we're considering a smaller change in time. But actually what we're going to eventually end up doing is considering such a small step in time that it's basically going to be 0. So we're just going to be considering d. Again, go back and watch my video on differentiation from first principles if that doesn't make sense to you. So how we can write this now is change in y over change in time. Oh look, dy by dt. This is just where my notation for dy by dt comes from. If you've never realised that, then congratulations. Welcome to the world of mathematics. So we've got dy by dt, and that's going to be approximately equal to y of t plus h. I'm just writing the same thing as what I've got up here. Minus y of t over h. Okay. Notice as well that t plus h minus t is equal to h. Yeah, so that is a change in time. So t2 minus t1 is t plus h minus t, which is equal to h. So t2 minus t1, that's my change in time, is equal to, so dt is equal to change in y, which is t plus h minus t, which is going to be equal to h. Works, all right, but I've just kind of skipped all that as just t. So, let's consider now different cases. Let's bear this in mind. Dy by dt is approximately equal to y of t plus h minus y of t over h. Well, what happens if dy by dt, so its left-hand side, is less than 0? Well, what does that mean? What does the right-hand side have to do in order to make this the case? Well, that has to be the case that if it's less than 0, this has to be less than 0 as well, doesn't it? So this y of t plus h has got to be less, y of t plus h, let me write it down. Y of t plus h minus y of t has got to be less than 0. Okay, which in turn implies that y of t plus h has got to be less than y of t. All right, let's consider the case when it's equal to 0. So when is it equal to 0? Well, that implies that the top is equal to 0. So y of t plus h minus y of t has got to be equal to 0, which of course implies that y of t plus h has got to be equal to y of t. And then the final situation is when dy by dt, so the left-hand side, has got to be, done less than 0, greater than 0. So that implies that y of t plus h minus y of t has got to be greater than 0. That's the only way that it can happen, which implies that y of t plus h has got to be, that's not equal to, that's greater than y of t. Alright, so those are all different cases. Why could I just ignore that h on the bottom? Well, because we've just taken h to be a small positive number. Right? So the very fact that h is positive means that it's not going to have any contribution to making dy by dt negative. It's always going to be the numerator that's going to have that contribution. And because we know it's positive as well, it can't be equal to 0. Or make this right-hand side equal to 0. It's basically not going to do anything. So you just basically ignore it. Alright, so these are all the different situations that you can have. I'll make this a little bit smaller for you, and I'll stick it over to the right-hand side. Okay, and now let's see what's going to happen. Now let's get to the good part. I might take a little bit of a break, kind of, so I can get ready to explain it to you. What's going to happen when we're going to plot our dy by dt as a function of y? So here we go. Yeah, I forgot to do something here. So now we've got this. Well, I haven't forgotten to do it, I just haven't done it yet. So now we've got this, I want to just basically consider what this means. So maybe if I make this a little bit bigger, just so that you can actually see what's going on. Actually, I'm going to... no, I'll make it a little bit bigger. I was going to rewrite it, but can't be bothered. So I'm going to make it a little bit bigger. Stick it over there. Hopefully that's all in screen now. That's all in shot. So basically, as dy by dt is less than 0, basically what we're saying is that dy by dt is decreasing. Yes, because it's less than 0. So basically it means that the gradient, dy by dt is the gradient. Yeah, when we differentiate something, we get the gradient. So the gradient is less than 0. So if the gradient is less than 0, we're going down like that. Okay, which basically means we're decreasing. So if we've got a function, basically means that the function is going like that. So it's decreasing. All right, and we've said that on the right-hand side that y of t plus h, the time period at... so we've got our same thing again. So we've got... so as y... as we move forward in time, okay, y will move to the left. Okay, because we're decreasing, so therefore we're moving to the left. And you can see this here. So our second point in time is less than our first point in time, which basically means that we're moving to the left. Yeah, does that make sense? Our second point in time is less than our first point in time. So if you consider it on a number line, say if this was 4 and this was 3, this is our first point in time, this is our second point in time. If our first point in time was... bigger than our second point in time, it basically means that we're getting smaller. So therefore we have to be moving to the left. Go away and think about it if you're not sure. So in this case, what basically means is we're moving to the left. If dy by dt is negative, we're moving to the left. Now let's consider the case when dy by dt is equal to 0. Well, if that's equal to 0, it basically means that we're not changing. It's just a single flat line. The gradient isn't changing, the rate of change isn't changing, so therefore we're not changing. All right, so therefore we just stay exactly where we are. And in this case, hopefully you can think about what it is, or you can work it out by now. It means that our function is increasing, so our gradient is getting bigger, so therefore our function is increasing. And this means that our second point in time is bigger than our first point in time. So if you think about it on a number line, if our second point in time, we start here, our second point in time is bigger than our first point in time, it basically means that we're moving to the right, because all the numbers to the right are getting bigger, and the numbers to the left are getting smaller. Okay, so therefore we're moving to the right when this is the case. Now we have got everything that we need to basically draw our phase plane or a phase portrait. All right, so let's say now we've got a function. We've got some function. I am going to consider it, actually I'm going to redraw those because that's not quite what I want. I'm going to consider it like that. Like that. I'm going to draw this underneath as well. All right. So, I've got a function, and it's going to be looking something like this. All right. Maybe if I just extend that, actually. That's better. All right, so this is my function. And I've got y on this axis, and I've got my derivative on this axis, so dy by dt. Because why is it derivative? Let me just show you. This is my y on this axis, like we had before up here. What was it? Here we had y on this axis. It's exactly the same thing, but now I'm just adding an extra axis. All right, and this is a function of y. Okay, well of course I've defined earlier that a function of y, my function of y, is just equal to dy by dt. Oh, don't do that. So my pen is disappearing. Let me just close it down to see if that works. Alright, hopefully that works now. So on this axis I've got my function of y. Well, my function of y I just defined earlier as dy by dt. Alright, so what's happening to this function? This is my function of y. It's happening like this. Well, hopefully you can see that here, okay, these are my equilibrium points. Because of course now, whereas before I'd be plotting like y as a function of x, now I've got an ODE. I'm basically trying to plot the ODE. So these are where my derivative is equal to 0. Are you happy with that? This is my like flat line. Okay, well this is 0 here. So as I read across, this means that dy by dt is equal to 0. This is what dy by dt, so this is dy by dt equals 0. So in other words, that's my equilibrium point. It's the point where my function neither increases nor decreases. It's a stationary point. Okay. Well, hopefully you can see that under here, to the left of this equilibrium point, let's call them A, B, and C. All right. To the left of this equilibrium point, my function is positive. My dy by dt is positive. All right. So if dy by dt is positive, let's consider this case. Dy by dt is positive. I basically move to the right. Actually, I'm going to plot them all at the same time. So I'm just drawing now on a single phase plane. So I'm just considering y now. So I'm looking at the solution. I'm looking at my graph, and then from this graph, I'm hoping to derive some solutions from it. Let me just make this a little bit bigger. So this is now y. So I'm just considering y and what's actually going on. So I'm simplifying it basically. So this is the point A, this is the point B, and this is the point C. And then I'm just going to consider what y is actually doing. So what y is doing over time. There's lots of variables going on, but hopefully you can follow the ideas. So this point is positive. So if dy by dt, if the rate of change is positive, then what does that mean? Go up here, the rate of change is positive. It basically means that I'm moving to the right. So over here, I'm moving to the right. So in other words, I'm moving towards this equilibrium point. Now let's look at this point here. Well, hopefully you can see that between A and B, my dy by dt is negative. Well, if dy by dt is negative, it means that I'm moving to the left. Okay, so dy by dt is negative. It basically means that I'm moving to the left. Now if I consider between B and C up here, well, that's positive. So if dy by dt is positive, between B and C, it basically means that I'm moving to the right. My y values are moving to the right as I move through time. And then if I consider just down here, sort of beyond C, let's just assume that C carries on going down way below this y-axis. It never turns again. And likewise to the left, it keeps on going up. So I don't only have to consider these. These are my equilibrium points. Well, what happens? It's negative. So therefore, we move to the left. All right. Now we can talk about stability. Next. Do I want to put in another video or should I just do it now? I'll tell you what, I will do it in another video. Okay, so what we've basically done is we've taken now, this is a phase portrait. All right, so we're considering each of the cases. We started right at the very beginning of why phase portraits are important to us. All right, and then we considered things like orbits and how y changes through time, and then we just plotted the graph. So we considered what happens with dy by dt, different cases, positive equals 0 and negative, and then we just basically plotted the graph of a function of y, which of course is dy by dt. We defined dy by dt against y, and we got this nice little graph. Saw what happens: positive, negative, and then from that we could then derive our phase portrait. So exactly what this is basically what our solutions, our values of y, are doing. Okay, so in other words, we haven't even solved the ODE. All right, we've just drawn the ODE, we've drawn that out on a graph, and we're able to tell exactly what those solutions are doing without even having to do any kind of algebra, any kind of horrible techniques whatsoever. We just have to draw it. And in the next video, we're going to talk about what this actually means to stability and things like that.